of Gerrit Hoogenboom from University of Florida. Gerrit had to address the question of minimal set of data that is needed to really achieve a good data collection that will be useful in the interpretation when we get to that stage, and also the FAIR principles, how to make the data findable, accessible, interoperable, and reproducible. Gerrit is professor and preeminent scholar at the Institute of Sustainable Food System at the University of Florida.
I really appreciate the invitation to present this webinar to you. So the title or assigned title of my webinar was The Need and Resources for Fair Data. And I've modified that a little bit to really talk about data, which type of data to collect and why to collect them, and giving a little bit of a perspective of crop modeling and data analytics, because that's my expertise. So when I think about farming in general, or as a farmer takes many observations prior even to planting to see how wet the field is during the growing season, looking at the status of the crop, and then also, of course, at the end of the season when you harvest your crop. So during all these observations, you analyze what you see, you might be collecting data, and then you decide on what to do. You might have to delay planting because of wet soil conditions in the field. You might be looking at your leaves that turn a little bit yellow, so you decide to apply fertilizer. So you really have to make a decision. And then once you make the decision, you need to act. So really what we're looking at is actionable information over time. And especially when we are talking about research by scientists, but in this case, on-farm research by farmers and growers, looking at not only actionable information, but we're looking at the data required to take that actionable information, which gets us back to on-farm experiments. We really want to understand how the farming system all fits together, because we have a complex system in which you operate. So then going back to the data part and talking more about the perspectives of modeling and data analytics. Traditionally in the agricultural research domain, we conduct trial and errors, replicated experiments where we vary fertilizer, varieties, or planting date, and then the data is being published and provided in extension bulletins for farmers to help them make more informed decisions. Now in the realm you're working in, you're really conducting the on-farm experiments, but it's not just about data collection. Really what we're interested in is doing data analytics, combining the experimental data you collect with some of the tools. And again, ultimately what we'd like to do is first of all understand, we want to understand what is happening in the field, why we see a certain phenomena such as stress in plants, possibly because of lack of moisture. You might see yellow leaves again because of lack of fertilizer. Then we want to be able to predict those conditions and ultimately get to control and manage for optimum conditions. And with respect to these options for adaptive management, we're really looking at risk reduction at the end, both the economic risks and the environmental risks. So then with respect to the data, what I show you here is actually a simplified crop model, how we see the crop modeling system from a mathematical perspective. And you see in the center, in the green box, what we call a crop model, but you can think at the same time of the type of data you're collecting or might be collecting in your on-farm experiments. We know that weather conditions play a very critical role from day to day and from season to season. But it's not only weather, it's also the soil conditions. We're looking at water holding capacities, we're looking at chemicals, we're looking at fertilizers. Looking at management, you need to decide when to plant your crop, which variety to plant, looking at your inputs. And then finally, we're looking at the genetics. You're working with different varieties, short season, long season, small seeded, large seeded. It all depends on the crop. What you're working with, if we know every year new varieties are being released by the breeders, and you then have to decide if you're going to adapt that particular variety in your field. So with respect then to the plant itself, and again, this is very simplistic, but we like to look at it first of all with respect to plant development. So it takes a certain number of days. We sometimes refer to that as physiological days, from planting to emergence, from emergence to flowering, and from flowering to maturity. And the growing season duration has a significant impact on yield. And if we move to the left part of this diagram, look at plant growth. So we know on a daily basis that the plant absorbs absorbs CO2 with light, and that results in carbohydrates, which partition to the different plant components. And ultimately, on the bottom, we get to yield at the end of the season. But it's not only yield. We know ultimately it's really about the economic components. We're looking at net income. There are production costs. You get certain prices for your products and byproducts that results in the net income. But it could also be at the same time restrictions with respect to resource use. If you're irrigating your crop, you might be limited to the amount of water you're allowed to use based on some type of state or government regulations. Or there might also be environmental regulations where you're limited to the amount of nitrogen you can actually leach back to the groundwater. So again, this is all a very complex system. So in order to deal with that system from a modeling perspective, but also from a data analytics perspective, we've defined what we call a minimum data set. So I've shown it here from a modeling perspective. In order to predict something with a computer model, we do require what we call a minimum set of data in order to operate that model. And depending on the model you work with, different models require different sets of data. But unfortunately, especially scientists have a tendency to ask for a lot of data, normally more data than they actually need. So with respect then to the definition of a minimum data set, we define it as a set that can be relatively easily collected under field conditions, including your field conditions in farmer's field, but at the same time also provide reasonable answers. And this is a very delicate balance with respect to the type and of amount of data we collect, and also this whole issue of reasonable answers. So the concept of the minimum data set has a different meaning for different people, depending on what type of system you're studying, if you're working with pests or diseases, or if you're trying to predict yield. So minimum data set can be defined as a particular use in mind. And I think with respect of the on-farm experiment community, we're really trying to understand the differences among years, among fields, among farms, and therefore we require a minimum set of data in order to understand those differences and then look at optimizing management strategies. Now, this whole concept of minimum data set is not new. You can see here a slide of a symposium that was held in 1983 in India. It was actually done again by a group of international researchers who at that time already were trying to truly define a minimum data set that could be used in the modeling community. So let us then take this back to on-farm perspective. So what you see here on this slide, possibly your farm, we have a particular field. I numbered it field 1. And we have 3 different yield levels. In 2018, we had a low yield. In 2019, we had a high yield. And maybe in 2020, we have an average yield. Nothing changed. Your soil didn't change. Your planting day didn't change. You grew the same hybrid or variety. So possibly then the differences can only be explained due to weather conditions. So maybe in 2018, low yield corresponded to a dry season. Maybe 2019 with a high yield, at a lower temperature, which may be benefiting a slightly longer growing season, and there's a higher yield, and maybe also a wet season. And then in 2020, everything was normal. Now we're looking at 2021, and we really don't know yet what the weather will be, because weather prediction models can only predict out about 10 days. So there's going to be very much uncertain. But it's not only about differences in years. Then you might have 4 different fields shown here, but field 1, 2, 3, and 4. Or maybe field 1 gives you low yield because maybe you have a sandy soil. Field 2 gives you a high yield because of a loamy soil. Maybe Field 3 is an average yield because of a clay soil, and then yield 4 that you're planning to rent. You don't really know what the yield is going to be, but it has a loamy scent. So again, soil plays a critical role in this whole system of trying to understand difference among yields. Then finally, you're comparing your yield levels with your neighbors. So maybe your one neighbor has a low yield because he possibly planted late and he had a short duration hybrid, while another neighbor, neighbor 2, had a high yield because he planted early with a long duration hybrid. And then another neighbor, neighbor 3, had an average yield with an average planting and a normal hybrid. And another neighbor, you don't really know, he might be planting an average planting date, but has a long duration hybrid, but don't really know what that type of yield will result in. So if we look at all that, trying to understand the yield differences with respect to minimum data, we define from a modeling perspective, but also I think from an experimental perspective as well, we first need to look at the environmental inputs. I mean, weather plays a very critical role, so we need to take some measurements, preferably for the temperature, looking at daily minimum and maximum temperature, looking at daily total precipitation, and looking at least at solar radiation, because we feel it's a very important component when we're looking at final yield. And the second one would be a little bit more static, although it could change over time with respect to the soil organic components, but it's just the soil data. You need to look at soil surface information. You might be working in a slopey field, so we need to look at runoff. You need to do a little bit with color, which has to do with albedo and reflection. And then especially permeability and drainage can have a big impact on the overall soil water balance. But it's not only the soil surface, it's also the individual soil layers associated with the soil profiles. It's highly likely that you have different soil horizons in your field, which have a different water holding characteristics. And again, to understand differences among fields, we need to be able to characterize that information. Might also be looking at nitrogen, I already mentioned organic matter, as well as other nutrients, all very critical parts of the environmental inputs. And then last but not least is going to be understanding the differences with respect to crop management. So if you're looking at, again, at yield differences, we need to know what goes in as input. Most cases, you know the crop and the cultivar. But again, the planting date can have a significant impact on your yield, depending if you plant early or if you plant late. I show spacing here, and we know there are different systems with different plant densities, so that has an input. Then we're looking at irrigation, depending on what type of farming system you have. If you work in if you grow in a dry area where you have access to irrigation, then the dates and amounts of irrigation become critical. Most people fertilize the crops, so again, it is important to take note of the dates, the amounts, and the type of fertilizer that are being applied. Same applies a little bit to tillage and other applications, especially when you look at chemicals. But this is only level 1, so basically these are the data that drive your system with respect to weather data, soil data, and crop management. Now we also need to talk about the observations and measurements. Now everyone measures yield because that's one of the outcomes of your farming system. But if the yields are different, what are we going to do? I mean, how can we explain differences due to weather, due to soil, and due to crop? So we possibly have to take additional measurements that could be related to grain size, the number of grains, possibly the seed filling duration as one of the causes. So we, at least from a modeling perspective, but also from an experimental perspective, we recommend that people also at least consider the yield components, which should be relatively easy to measure, which would be at least either grain size or grain number or 1,000 grain number. It helps you determine a little bit what the differences are because of yield and weather interactions with soil and crop management. More challenging would be to look at the harvest index, but again, it's also an important observation. This would require some type of final biomass observations, so you can calculate the ratio of the yield over the final biomass to get to the harvest index. Then the next one would be growing season duration. We feel that development of the crop over time also plays a very critical role in understanding yield differences. So in most cases, we recommend at least to measure or record physiological maturity or harvest maturity, but possibly also look at flowering date, because the number of days between flowering and physiological maturity provides you with information with the grain filling duration, which is quite critical. And then finally, we have another level, what we call issue or problem oriented. This is another requirement, but if there are issues with respect to drought, you've measured your precipitation, you know your irrigation, but there's still drought issues, then this might require that some type of soil measurements are taken. In most cases, we recommend that soil moisture is measured at different locations, possibly in the field, and preferably also at different soil depths over time. So you can see the close interaction between changes in soil moisture in response, first of all, to plant water uptake, but also to rainfall as well as irrigation. If nutrients are an issue, then we highly recommend that at least some type of soil nutrient measurements are taken. Most people might take a grab sample prior to planting, look at fertilizer recommendations, but maybe if you have serious issues with nutrients, this might require that soil nutrient measurements are taken at different depths, maybe at planting, and maybe one set of samples at final harvest to look at differences and to really fully understand what's happening in the field with respect to possibly nutrient deficiency. In parallel, then you might also want to take measurements related to especially deficiencies in nutrients in the leaves. They can be taken over time, and there are currently some sensors even that allows you to take non-destructive measurements that are then being used to provide fertilizer recommendations. So then to summarize really the minimum data for understanding and trying then use that information to make decisions is to first of all have the on-farm data with respect to environmental conditions and crop management. This is the true minimum. And then with respect to the observation itself as it relates to the crop, shown here in priority somewhat. Of course, you all have access to yield. But the next one would be phenology, the maturity dates. So you can look at the growing season duration. Then we would recommend the flowering date, then possibly yield components, and then maybe number 5, looking at final biomass that allows you to calculate a harvest index. So to summarize this, with respect to different levels, so level 1 would be minimum input data that drive the crop production system. Level 2 would be the minimum observational data to help you explain the differences among years, fields, or management practices. And then level 3 would be the type of data that allows you to really look at specific issues such as drought stress or nutrient stress. So my title also had a component what we refer to as FAIR data, and FAIR is a fairly new acronym as it relates to data. It's become very common in experimental research, but I think also in your setting, it becomes important as well. So the F stands for findable. So especially if data being recorded and stored in an electronic databases, we want to be able to find the data. But not only find them, we also want to be able to access the data as well. And then interoperable means that if you collect data and your neighbor collects data and you do use some type of data analytics, then you want to make sure that the data analytics tools you're using can access those different databases. And reusable in this context means that you might be conducting your first set of data analytics on your data, but then you might want to combine it again with your neighbor's data or combine it with data from other resources. So reusable means that we can use and reuse the data multiple times for data analytics. Some of this also links back to some of the earlier presentations from today. There was one presentation on data agglomeration and data analytics. So the fair data and having access to fair data play a very critical role. Some of my personal work in the realm of modeling and decision support systems and tools, again, fair data play a critical role as well. And ultimately, what we would like to get to is really actionable information that allows us to look at improved management that ultimately will increase the income on your farm and also minimizes the impact on the environment. So possibly the future farm might look like this, and this is my final slide, that we might be monitoring each individual plant, look at all the data that are provided by the plant, and really the plant is the integrator of your farming system. And if you have sufficient data, that allows you then to look at precision management to make sure that each individual plant produces yield that ultimately maximizes your income. So again, I really appreciate the opportunity to present this seminar to you and to talk a little bit about minimum data in the concept of on-farm experiments. Thank you.